So yeah, as mentioned, the title of this work is Bridge Deterioration Tool Using Neural Networks. Let me get some light in here. It's kind of dark. One moment. Okay, hopefully you can see me. Okay, yep. So my name is Tobby Lie. My mentor's name is Farnoosh Binay Kashani. We come from the Big Data Management and Mining Lab at the University of Colorado, Denver. So here's a brief outline of what we're going to talk about. First, we're going to talk about sort of the motivation behind this project, this work, sort of like the key observations we observed at the very beginning of the work. And then we're going to go into a problem definition where we formalize the work and sort of talk about what's the main problem we're addressing and the formal definition of it. We're going to talk about the data that we utilized in this work specifically. Then we're going to get into model details. Since we are using a data-driven approach here, we want to talk about sort of how did we construct the model, some key concepts there, as well as how did we evaluate the model success. Then we want to get into a system demonstration. We took these models that we developed and embedded them into an actual software tool. So we're going to go into that and sort of where it's at in development, and then talk about some future work in two key areas, which is the system that we just mentioned, and then also want to talk about a new method that we are attempting in the future, which is called physics-guided neural networks. So first, start with some motivation. We noticed some key observations at the very beginning of the work. One of them was that there were very many different quantitative sort of descriptors or factors that affect bridge deterioration. And we also noticed that from the literature, bridge structures tend to deteriorate even faster the older that they are. So over time, this deterioration process for bridges actually accelerates the older a bridge gets. And so we noticed that every year or every 2 years, on a frequent basis, bridge report data is collected across the United States. So this data comes in the form of like sufficiency ratings, condition ratings, daily traffic statistics for certain bridges. We noticed that this data is collected and structured in an accessible way. So we wanted to leverage this data to create some sort of predictive model. So here we came up with the idea of IBM, which is Intelligent Bridge Management. So we wanted to leverage deep learning, so neural networks, which are a type of data-driven model, which will leverage this type of data to create predictions. So what's the problem definition or formalization? Essentially, it's being able to provide predictive analysis or forecasting of deterioration patterns within bridge structures by way of quantitative descriptors. So for example, given a set of bridges with condition ratings over time, we want to be able to create a model that uses these features or variables to be able to predict them in the future. I'll quickly talk about the data that we utilized. So the first data source was actually NBI, which is the National Bridge Inventory. And this is annually collected bridge evaluation data that's collected every year for bridges across the country. And then we also leveraged the National Oceanic and Atmospheric Administration data, which is essentially just a climate and weather data set that is collected for things such as precipitation averages, snowfall averages, and snow depth averages, either on a daily basis or a monthly basis and a yearly basis. So we use this to sort of supplement that first data set. And then we also collected Colorado-specific transportation data. So that essentially just means there are different routes in Colorado that are recorded for average daily traffic and statistics such as that. And so we collected this information as well to sort of integrate with our two data sets prior. Let's talk about model construction. Before we get into this section, I just want to talk about sort of the form of this data. So essentially, we're dealing with a multivariate time series problem. And essentially, our models will take in many years worth of multiple variables for different bridges. And then the output of that is condition ratings across time within the future. So model construction, we went with 3 different classes of models. The first being traditional regression-based machine learning models. I won't go into too much detail, but these were sort of the bare baseline that we went with to sort of compare our more novel solutions to. So you can see there's stuff like ARIMA modeling, double exponential smoothing, multiple regression. And then we also examined some baseline neural network models. So these are models that are still on the simpler side, but more complex than the machine learning models. And we're actually going to go specifically into the feed-forward neural network, the convolutional neural network in a couple slides coming up. And then our most novel or recent sort of innovations within data-driven time series models are the multi-channel CNN and then the TCN, which is a temporal convolutional neural network. And then we're going to get into the TCN as well in detail coming up here. So just a brief background about sort of how neural networks work, what they are on a high level, just to give some background and context. Essentially, this is just a statistical model which has these things called nodes internally in them. So here at the input side of the model, we have some input nodes, which take as input the data. And essentially, a series of matrix multiplications occur within the hidden nodes, which are what these middle intermediate nodes are called. And a bunch of matrix multiplications occur, as well as what we call activation functions, which provide sort of like a nonlinearity to the inputs into these nodes. And it sort of gives you a status or sort of like a gradient of how active a certain node is in here. And by the time you get to the output side, there's sort of like a voting system is what you can think of it here in sort of the intermediate nodes. And based on how active certain nodes are, it'll give you a certain output. And this output is sort of a reliable prediction that we expect for the problem that we're dealing with. This is sort of just talking about what I went through there in the previous slide. And then at the end, once a prediction has been formed, something called a cost function is utilized, which essentially will take that output, compare it to some actual ground truth data point, and give you some sense of error or loss. And this will tell you about how good or how bad a prediction is at prediction time. And then a process called gradient descent is utilized to sort of propagate this error back into the model. And essentially, in an ideal case, we have a model where all of these weights and nodes are in an optimal position to predict reliable and confident predictions. And that's just talking about the back propagation. And essentially at inference time, we freeze all of these weights and these nodes once we have come up with a sort of confident enough point within the model. And we freeze these weights and we essentially just run input data through and provide predictions. And essentially for training, you have a training phase where all of these weights are updated. And eventually, once you're satisfied with a certain confidence level of the model, at inference time, to get a prediction, you will actually freeze these and then start obtaining predictions. And this is some formalization on that. So essentially we have in a feed forward, it's just a series of matrix multiplications, as you can see here, with the application of some activation functions for the nonlinearities. And then here, the y-hat is your actual prediction. And then in addition to that, we actually will update the model weights using what we call the gradient descent and backpropagation. And this is sort of the formalization for that. So you have a loss function, you take the negative gradient, and you update each of the weights. And then here, we're going to talk about CNNs. So CNNs are one of our more successful models that we experimented with. And essentially, these are just neural networks, but more specifically used for grid-like data traditionally. So here we have sort of a grid, and we have what are called kernels or filters, and they just run across this grid and perform sort of some weighted sums. And we have a series of filters typically that will give you some sort of embedding or understanding of the input data. And here you can think of this matrix as sort of like the rows are your time steps or years worth of bridge evaluation data. And then your columns are each variable for that time series. And that's how we input it into the model. Here, we'll talk briefly about a TCN. It's essentially just a CNN, but more specialized for time series. Here you can see we have these pairwise embeddings. And based on these pairwise embeddings, we have what are called dilated and causal embeddings. And so essentially that just means that these intermediate embeddings, they build up to the final output, and the output can only see sort of historical data. And the dilation rate is sort of how wide of a receptive field we can have within sort of examining the data. And then let's talk about model evaluation. So essentially we have NBI data, NBI and NOAA data, NBI, and then that ADT data that I talked about. So essentially we had different splits of this data set, which of course come with different sizes of samples. And we experimented on different combinations of the input data that we were able to acquire. And then we actually use RMSE as our evaluation metric, which is root mean squared error, which we'll get to in a couple slides here. And as I said before, we have sort of a training phase and a testing phase for the model. So we have that 60-40 ratio, which is what we utilized. We did some normalization on the data. And again, we are conditioning our model on multivariate time series data and forecasting future condition ratings. So brief talk about RMSE. Essentially, this is just sort of a way to measure error within our test set of our data. So essentially, this is the formulation for it, but it just sort of measures the distance between data points for predictions and actual points, and it gives you sort of an aggregate measure of that across all of your samples. And the lower this value is, the better. So just a sort of illustration of what we mean by train and test. Say we have a total of 7,000-ish points. We will split up the train data, maybe 60 or 70% of that, which is around 5,000 samples. And then our test set actually has around 2,215 samples. And this is where we'll actually get our RMSE score. So within this test set, you'll actually derive real predictions, and then you'll gain an aggregate measure of performance. And that's how we evaluated our data there, or our method. And there's a lot of numbers here, but I just want to briefly talk about some of the results that we were able to get from our modeling. So you can see here in the CNN and the TCN, it performed pretty well across the board, actually, and most consistently. This is just on the NBI data only. So you can see there's the line here for CNN and the line here for TCN. This is the NBI with NOAA. You can see a similar trend here for the CNN and TCN. This is NBI with Otis. You can see a similar trend there. I don't want to spend too much time on the numbers, but it's essentially you can see the same trend as the CNN and TCN performing best when measured against RMSE of the other models. And here we had an exceptional case of double exponential smoothing, which was one of our actually baseline regression models. It actually did perform the best, but one thing we noted here is this is actually a univariate method. So it's not able to take into consideration multiple variables for a prediction, and it also can only view one time series at a time. So the good thing about neural networks is you can sort of gain an aggregate understanding across multiple samples, whereas methods like this can only look at one sample at a time individually. I just want to do a quick system demo. So I'm going to switch here to our system. It's still a work in progress, so the sort of interface might be a little bit messy. But essentially, we have what's called forecasting and bridge family generation. Bridge family generation I'll start with. Essentially, we're working on sort of an orthogonal component of this sort of analysis software, where we're talking about the generation of clusters or bridge families based on either variables or performance of bridges. So for example, here I'll go into bridge families based on features. And you can see here, we have a dropdown where we can sort of select like what sort of features do we want to obtain clusters or bridge families out of. So say we want to take a look at like deck area, we want to take a look at maybe deck protection, and then we want to generate certain bridge families or clusters. We can do that here. And it'll actually generate like a list of bridge IDs, and then also sort of like what cluster they belong to. And actually, there's another way to do this, which is based on performance. Here again, you can take a look at maybe based on average daily traffic, you can generate a certain number of families. You can click the generate family. And here you have sort of like time series where you have certain clusters based on different subsets of bridges based on different features or performance ratings. And then if we go over here to the forecasting side, more so what the slideshow is talking about, we can actually go to forecast, where we can say, well, I'd like to forecast condition ratings based on weather data, as well as bridge evaluation data. And let's say I want it for the next 3 years. I can hit forecast. It's going to do some stuff in the background based on the models that we talked about. It'll give us a sample set of files here. So say we want to look at deck condition ratings specifically. Here we have, for example, the first column is a series of bridges. And we also have, in our case here, we have 21 input time steps. So this is sort of what our models are being trained on. And then we have 3 future time steps here that we requested predictions for. So these are numerical, sort of stepwise predictions in the future of what we expect these to be. And this is these are generated from our model. And then just one more thing, one more feature here. We have sort of a retrain module where we can sort of refresh these models dependent on if there's new data that appears within these data sets. So for example, say I want to check for new NBI data or new NOAA data. These are all data sets that exist online. So they have some sort of API or way to access them. So we've actually implemented what's called a data scraper to actually go out and retrieve this data automatically. So we can do that. And then we can also retrain our bridges dependent on if our clustering algorithms created any clusters of interest for us. And then also we noticed that there were some bridge samples that showed condition ratings that were not monotonically decreasing, meaning there may have been some sort of maintenance or repair in the middle of the timeline, for example, which causes a condition rating to increase rather than decrease. So if you want to remove any instances of those repaired bridges, we can also click yes here. And then you just have to hit retrain, and it does all of this in an automated way. I won't go through that end to end because it does take some time. But back to the presentation, I just have one more slide, and that's on future work. So future work, again, as I mentioned in the beginning, it's twofold. We have future work in the software tool that we're building. This is sort of like a high-level system design that we worked on at the very beginning. Has a couple components here. Some of them are already in there. For example, we can request an inference for like forecasting. We can train models from scratch, but there's some other stuff in there. Like if we find an additional data source that may perhaps be complementary or supplementary to our system, we can add that. We want to add an interface to be able to do that. And then also if we want to experiment with certain models or new variations of models for these predictions, we want to create an interface for that, for example. And then the very last slide is just, I just want to briefly touch on physics guided deep learning, which I think might be a pivotal sort of part of this work in terms of actually obtaining more reliable predictions. So as I said previously, the models that I talked about before are more so to statistical or probabilistic models that rely solely on data. Essentially, physics-guided deep learning will leverage both that data-driven approach as well as actual physics functions embedded within the model itself, so that we can actually hope to obtain more realistic results within physical systems simulating, as it may in some cases within purely data-driven models, they have a tendency to sort of predict or output predictions that are not consistent with actual physics or laws of physics. So this is sort of another direction that we want to take moving forward that we've actually begun. But essentially, that's my last slide. That's all I have for this work. Thanks for listening in.